I'm going to go ahead and open up our poll questions and get that out of the way before he gets on. Okay. If you guys just want to take a few seconds to answer each one of these as they come up, that'd be great. Okay. Do the next one. Okay. And the last one. He said he'd be on about 5 after, so we'll give him a little bit of time here.
Hey guys.
Hey, Sukumar.
Hey, I'm the presenter, right?
Yes.
Okay.
Okay, go ahead.
Share my screen. Are we all set, Sarah?
We are. Everyone's listening.
Alright guys, this is Sukumar. I'm here to do your BMX webinar real quick. Just giving you a quick introduction. Work with CDT. Do a lot of simulation stuff. CDT is a Barry-Wehmiller company. I work as an engineering manager now with them. And I guess you guys done with the poll, so let's go ahead and get it on, get it started, right? So here, with respect to BMX, wanted you guys to kind of see that I'm going to talk about the basic BMX stuff. I'm going to talk about an Excel feature analysis where I use an Excel file to demonstrate how ProE and Excel work together. I could also use MathCAD, but then I realized that not a lot of people use MathCAD, so I wanted to show it with respect to Excel. Wanted to run feasibility analysis, wanted to run optimization, sensitivity studies, use FEA and how BMX and FEA work together, use how mechanism and BMX work together. So with that said, let's get started. With BMX, most people the most often ignored part of it is that there is fit, form, and function, and we are so involved in with respect to the fit and the form that the function part gets often ignored. And we run finite element analysis per se, but then design optimization is slightly different than structural optimization. What we are going to talk about with respect to BMX is design optimization. Say for example, if this is a bicycle, I'm trying to simulate the weight of the person by adding a mass over here, okay? And if this bicycle has to function the way it's supposed to, its center of gravity needs to be at a certain place because all the weight acts at CG and you want to make sure it's at an optimal position. So in terms of the bike right here, it's two wheels, so I would rather want the CG to be right between the two axles. So here I have two planes at the two axle points. So I'm going to go ahead and find out where my CG is and where my CG is supposed to be. So I'm going to create a plane, just offset it so that it's right in the middle. So I know the distance is 24. So that's where I want my CG to be. But where is the CG right now? So you can go ahead, run a quick analysis. So you go mass properties. And note that it kind of shows you that's where my center of gravity is. What I can do is I can quickly save it as a feature. I can also add some feature parameters if I choose to. I can also create a point at the center of gravity. Alright, so let's display the point and make sure the point tags on. And that way you can see it. So that's where the current CG is, and I want that CG to lie on this plane, which is exactly halfway between the two axes. Now, center of gravity depends on weight or per se volume, right? So how are you going to determine which dimensions to change so that the CG moves to the required position? So before you make all those changes, we want to see where the CG is and where do you want it and what is the distance that you have to move the CG to. Again, I keep saying CG, CG implies center of gravity. So I go ahead and measure the distance. So I want to measure the distance from the point to the plane. let's see the distance is 3.24 inches. Now, if you are using Wildfire 5, you can do the exact same thing. If you're using Wildfire 4, 3, 2, you can do the exact same things. When it comes to Creo, there is a slight difference. Now, the difference is that you see a button right here. You want to check that and make sure you show the feature tab. In Wildfire 4, 5, so on and so forth, this feature tab is shown automatically. But now you have to show it from here in Creo Tools, hidden by default. So here I want to create a parameter called distance. So I'm going to just copy it and I save this analysis. So you see in my model tree I have a feature called distance. And what is the value of this distance? Instead of you always doing an edit definition trying to find out what the value is, you can go ahead and look at 3 columns, feature parameters, type in distance, and say OK. So that's the value of that distance. Alright, so I need to move that distance, or I need to minimize this distance to pretty much 0. Alright, so I want to change some dimensions. So how do I find out which dimensions to change before I even make the change? Now for that I run something called a sensitivity analysis. This exact button is available through the analysis drop down in Wildfire 3, 4 and 5. Right? You say analysis, sensitivity analysis in the other older versions of Pro. So here I'm going to select a dimension. So I say I want to select this angle. I want to change it from say 65 to 85 degrees. And the parameter that I want to plot is distance. And I want to run it in like about 5 steps. So when you hit compute, it's going to give you a nice little graph telling you as you change that angle, how does that distance parameter change. And it also tells you at what values your model might fail, as you could see right here. If this graph ended up being a straight line, that means no matter what you change the dimensional value to, it is not affecting the parameter that we are worried about. So I would rather not use that dimension in my optimization. So you can see this is for the angle dimension. You can obviously go ahead and pick any dimension you want. So you're going to pick 27 and say I want to vary this distance or this dimension from 24 to 30 and compute it. So you can see as that distance being reduced, you approach a value 0. So this dimension and this dimension are sensitive to the parameter distance. That's how I decide which dimension to use in my optimization. Now that being said, let's go ahead and see if we can optimize it. Now when you optimize, you just go analysis optimize in Wildfire 3, 4 or 5, and here there's a little button right below the sensitivity studies. Now when you optimize, you have a goal. If you know that you can achieve that goal, then you run an optimization. When you run feasibility, you're trying to find out if a solution is possible or not. If you're not sure about it, then I'd run a feasibility study. Okay, so here I want to add a constraint. I want to see if this particular design is feasible, right? So I'm going to go ahead and say distance is supposed to be 0. I want the distance to be 0. I can also use greater than or less than symbols so that I get it to a range of values if I want to, or I can go exact value 0. Now, in order for me to do this, I want to go ahead and change certain dimensions. So you go ahead, add a dimension. I pick that 27, I pick the 72, and I can pick another one right here. Here, I'm going to give it ranges, say 24 to 30. And this one I'm going to go from 75 to 85. Oops. And here we'll go from 14 to say 18. Now, what you also have to be careful about is that when you choose multiple dimensions, you have to make sure that a change in one dimension does not neutralize the change caused by another dimension. Okay, so you have to be careful about that. And then, you're going to go ahead and hit compute. So now it's going to run through the optimization, give you a little graph which tells you, hey, am I approaching a value where I am reaching 0 or not with respect to this? So give it about a couple of seconds. It's going to go ahead and as you can see, it shape animates and tells you that, hey, I found a feasible solution where you can see the value of the distance. It is 0 and at these values. So at 25, 76.9 and say about 18 point something or 16 point something. So if you like it, you go ahead and say close, and you can say confirm to keep it. You can undo or cancel if you don't like it. So you say confirm. Now here is where the CG is exactly between the two axes, and that's probably your best design in terms of function of that particular product. Is that fair enough? So what do we do in a typical BMX process? We go ahead, run our initial analysis to find out where certain values or where certain parameters are. The moment we do that, we go ahead and see, okay, for a certain change in a dimension, how does this particular parameter get affected? If the dimension is going to affect the parameter, we will use that dimension in our optimization. If the dimension is not affecting the parameter, then we will not use the dimension in our optimization. So once we determine the dimensions, we go ahead, run an optimization study where we say, hey, I want the distance to be equal to 0, and I'm going to change these dimensions over a certain range. This is very similar to structural optimization, but this is actually design optimization. Alright, so that being said, that was a brief overview of what BMX can do. It can do a lot of complicated things. So that was just to kind of kickstart and kind of give you an idea as to what BMX is and what BMX can do. Again, BMX is Behavioral Modeling Extension. Alright, the next thing I want to show you is the Excel feature. So here I have an example of an airplane wing. Right? And I want to see at what angle of attack do I get maximum lift, right? So what I've done is I've run an analysis for area. It's basically measuring the area of the wing, and it is projected area. See that? It's projected onto this plane. So if you look at the wing in this direction, what is the value of that area? And you see that you have created this little parameter called projected area. Copy. We can go to our three columns, feature parameters, paste it, and you get to see the value. Now you can see, you can go ahead, edit, change the angle. Right here I want to make this like say 5. And you can see the projected area is 125. If it was 10, the projected area is 149. So now I'm going to find out at what angle of attack do I get maximum lift. Okay. So we have an Excel file where we have all our calculations done. I'm going to show you how to relate an Excel file with ProEngineer. So here we go into the Excel file and quickly look at this. Alright, so here's my calculations. Here's my equation. So I'm putting in a projected area, I'm putting it in an angle of attack, and then I have my speed and wing velocity right here, and it gives me the lift force. Now notice that because I'm using MathCAD, I have to be super careful as to using the right unit system. Excel does not have unit system, right? So you have to be careful to make sure you are putting the right units and the right values. If you were using MathCAD, you could put the units in any value or any unit system, and you can get the answer in any unit system. That's the advantage of having MathCAD. But again, here we are using Excel, and this is my little Excel sheet that does the calculation for you. Okay? So now, how do we run an Excel analysis in Creo? So you go to Analysis, you have Excel Analysis right here. Click on that little button. Now, you can load a file. So this file's right here. All right, you see that it opens it up. All right, so I want to push a dimension from ProE to Excel. So I say add dimension, and then I pick that angle of attack and say I want this angle of attack to go right there, and say done. So you see I've related dimension D17 to cell E16. So I can relate each dimension to each of the cells in MathCAD or in Excel like that. I can also add a parameter and say projected area. I want projected area to be entered over here. Projected area, and then say done. Now I want to read from MathCAD, so I say output is that. Done. So that's the output. So you go ahead and compute it. So there you go, it tells you the value. You can go ahead and add a feature. You can say force is the name of the feature and close it. So you can do an edit definition here just to see if everything is the way you want. So you see force, it's an Excel analysis. You see that you're pushing and pulling these data in there, D17 and projected area. You compute it, you close it. You see that you're reading a parameter named XL37, so you want to give it a name, say lift. That's it done. Now, what is the value of lift? If you go 3 columns, feature parameter, if you say lift and say OK, there it is. It's reading from Excel. What can you do with it? Okay, I want to see how I can change the value of angle of attack, which controls the projected area, and see how much lift force I would need. So I can run a sensitivity analysis where I say the dimension that I want to vary is right here. I want to vary it from say 5 to 30. The parameter that I want to plot is the lift force and say compute. So what this is going to do is it's going to tell you as you change the value of the wing's angle of attack from 5 to 30, how is the lift force changing? You see at around 15 or 17, the value is maxing out. So that's a good value. So you place your cursor, it says when it is 16.11, the lift force is the highest. So you go ahead and then optimize it. So you say optimize, I want to maximize the lift force. All right, you want to add this and say I want the lift force to be say greater than 7,600. So I want it to be at least 7,600. The dimension that I want to vary is this. And now, because I know the value is somewhere around 16, I can give it a range from say 15 217. So what this sensitivity study tells me is if I should use the dimension for optimization, and if I'm going to use it, what is the value or the range for it. The smaller the range, the faster the optimization. So I go ahead and hit compute. So it's going to give me a nice little graph and tell me that, okay, here's my first level of optimization. And it tells me that that's the value that I got. So you go close it, confirm it. You see, that's the max lift forward we're hitting at 15.27. All right. So this was working with Excel and Pro E to do analysis. All right. So the next thing that I want to talk to you about is the simulate feature. So a lot of people run finite element analysis, and also, I'm a designer. I don't know how to run finite element analysis. Somebody else has run this finite element analysis, and I want to make sure that when I make design and changes, that I'm compatible with the allowed values. So here I'm just going to hop in real quick into Creo Simulate, and you can see that I have some bearing forces pulling and pushing from here, and I have these constraints right there that are stopping, right? So I have my analysis done, and I can go ahead and look at results. I can animate it to kind of see what's going to happen. Okay, you can also see the max stress right here at the very top is 97. Let's say my allowed value is 110, whatever. We just throw in a random number and say, hey, my allowed value is 110, so I'm allowed to make some design changes or whatever. Now, what you can do now is you can get into analysis, say new analysis. You can give it a name, say structural analysis. Say this is a Creo Simulate analysis. Hit next. You see that it reads from the existing analysis right there. You have run a bracket static. You go ahead and compute it. So it's going to quickly run that FEA analysis for you. And it's going to give you all the results for it. So you can see the maximum von Mises stress is 97. So you go close it and say done. Now what is the value of this von Mises stress? So you go 3 columns, feature parameter, say max stress Vn, and say okay. So that's your maximum von Mises stress. So now let's make some design changes. Okay, I want to change this angle or this radius of the round. So I want to go sensitivity analysis, pick a dimension, say hey, I'm going to pick that, and I'm going to run it in about 5 steps. And I want to see how my, see the list of parameters that I can plot, how my von Mises stress is going to change. Right? So I'm going to run it from say 45 to 60 and say compute. So this is going to come back and tell me what is my von Mises stress and what is the value. So you see really quickly that at around 45, my stress value is about 127. My allowable is 110, which is somewhere close to 48. So the max I can go to is 48 in terms of my design change. If I go more than 48 and make it, fine, but it is not going to be within the allowed values. Now, let's say, you know what, I want to go ahead and increase the angle. So you can see, okay, so my stress values are decreasing as I increase the angle. So you can see, okay, max value is 110. You want to be somewhere close to 48.5, and you don't want to go below that because that will break your max value. So even before you run a design change, you can quickly find out if that design change is even going to be valid or not. So this is how you can work with finite element analysis, and you can work with respect to BMX and Pro Engineer. Now, the next example I had for you guys is a fuel tank optimization. So a lot of people have been asking me this question, so I wanted to go ahead and throw this out there. So here I have a fuel tank. All right. Now, what I'm going to do is I need to measure the volume of the fuel tank, and I want to like kind of create markers on it. Right. I want to make sure that I mark it at the 2-gallon level or a 10-gallon level or a 10,000 level gallon. So I'm going to drag this all the way up, right? And I'm going to go ahead and create a datum plane for my measurement purposes. So let me go ahead and see. That's my top plane. So I'm going to go ahead and go down like that, say about 24 or whatever. All right. So now I'm going to go to the analysis, run my mass properties. All right. You see that? It tells me what my volume is, what my surface area is, what my density is. I can click on information. It gives me my radii of gyration, moments of inertia, all kinds of details right here. Now, another way to also achieve the same thing is you can go here and say measure the volume. So I'm more specific to only the volume. It tells me the overall volume of the fuel tank before it's being shelled. Now I can also go ahead and say, pick the plane that we just created and say, I want the volume from the bottom of that plane. See that I flip the arrow down. That's a one-sided volume. You can go ahead and see that it's creating a parameter called U for say one-sided. You can go ahead and save this feature. I'm going to save it as solid. All right. So then I'm going to go ahead and say shell it. I'm going to redo the exact same thing to measure the volume after it's being shelled. And we want to look at the one-sided volume of this. We're going to go ahead, look at the feature that it creates, and then I'm going to call this feature shell. Now, what is the volume of solid and shell? So here I'm just going to go to 3 columns, feature parameters, and I paste this one-sided volume parameter name. And that tells you what is the volume of solid and shell. Now, what is the actual volume of empty space? The volume of shell is actually the volume of the material left. So unless I do solid minus the shell, I won't find out what is the volume of empty space below this plane. So for that, I need to run an analysis right here. So I say, let's say this is like an oil tank, right? So I'm going to name the feature oil and say that this is a relation. And I go to the next slide, and here I'm going to say one-sided volume colon FID underscore oil. So I'm going to just go ahead and paste it on, like, say, Microsoft Word or something. And that way I can like make it zoom bigger. So let's go say, okay. So as you can see, it says one-sided volume colon FID oil. So what I'm trying to say is I want to know the one-sided volume of feature ID oil. This is equal to one-sided volume of feature ID solid minus one-sided volume of feature ID shell. Fair enough? So one-sided volume colon FID is, this is the name of the parameter, colon feature ID shell. Right? So here, I'm going to go back here and paste this, verify that my relations are okay, and you can see that's the volume. And you say okay, and done. All right, so now I want this plane to be at 200,000. I want this plane to mark where it is 200,000 in terms of volume. So what I can do is I can go run a sensitivity analysis where I select the dimension, which is this dimension, which is offset from the top plane. So obviously I need to push it down. So I'm going to go from 24 to 30. And I'm going to look at the parameter one-sided volume of oil. Do it in 5 steps. Compute it. Now when I'm doing this, you see that I kind of find out that at around 29, so at around 29 to 29.5, I am hitting 200,000. So when I optimize this, my range is not going to be from 24 to 30, it's going to be from 29 to 30 or 29.5. Right? So I quickly go feasibility, add a parameter. I say one-sided volume of oil needs to be equal to 2E5. Fair enough? 2E5. And then the dimension that I want to vary is there. I want to vary it from, say, 29, maybe let's just say 30. All right? And then hit compute. So it's going to tell me at around 29.33, that's how close it gets to 200K. You can say confirm. Maybe if you want to edit, I think around 3, 4, you get pretty close when you start moving that. All right. So depending on your accuracy, you can get really close to that value, or you can go, exactly to that value. So you can see 200.127. So you can change it, or you can re-optimize it however you want to. I just wanted to show this as an example and see how relation works. We spoke about optimizing for CG. We spoke about optimizing for volume. We spoke about optimizing for forces and stresses using FEA and Excel. Fair enough? Another last example that I had for you guys, and then we'll open for Q&A, would be volume in terms of a hand pump optimization. So here I have a hand pump. Right? So this is my hand pump. And I'm going to go ahead and show you. That's what I'm trying to do. Right? So I want to go ahead and find out how can I improve or increase the volume that gets pumped per stroke. For every stroke, I want to find out how can I improve or increase the volume of whatever fluid that this is being used to pump. So I have a mechanism analysis. I'm running this analysis as a position. See that? I'm just going to say run. That's one stroke, right? I'm just going to limit it to one stroke. All right. So let's get here, say features. So I want to see, the first thing that I'm more concerned with is the valve height. So how do I measure the volume of whatever water or oil that's coming in there? So I have a distance measurement. You see that I'm actually measuring the distance from the bottom surface right there to the top surface of the piston right there. So that's the distance that I'm measuring between that surface and that surface. Okay. Now, I also go ahead and want to make sure that there is enough clearance between this part and this part. So here, if I do a definition, I'm just going to pick the top of that and the top of the cylinder and say, what is the clearance value? So here is the clearance. So notice that it also creates a parameter called clearance for you. So you can go ahead and say 3 columns, feature parameters, what's the clearance value, right? So 0.73 is the clearance. Now, I'm going to also go ahead and say, hey, you know what? The mechanism analysis that we just ran, so it's a new analysis. Instead of Excel or Creo Simulate or relation, I'm going to say motion. I say next. You see that it's going to calculate the distance y value distance, which is the distance from here to here in the y direction, and the clearance through the range of motion. What is the clearance between this and this? So you can go ahead and run this analysis real quick. So it kind of tells me that is the clearance, right? You see the minimum clearance is 0.7, and then the, as it goes up and down, it kind of changes. Then this also tells you the distance that the piston travels, right? It goes from 2.75 to 12. That's how much the distance between these two parts vary during one stroke. All right? Now, so that's your range of motion. So what is the volume? What is the volume of oil coming in? It is the current distance times pi, which gives you the volume of the cylinder, minus the maximum distance minus 5. You see this in the relation real quick. So see, it's a new analysis relation, which is what we just did. It's just a volume relation. You see, it says that the maximum distance in the range of motion times the minus distance, in terms of pi. Right here, it gives you just a cylinder volume, nothing fancy right here. You're just saying we are taking the difference between the maximum distance between those two components minus the minimum distance. So you actually get the distance it travels during the range of motion, and then you multiply it by pi to get the volume. So that's the volume, and you can also find out what is the current volume. So let me just do real quick, and there you go. So now, what you want to do is you want to go ahead and optimize it for maximizing the volume, right? So you want to run a feasibility solution. Oops. You want to run a feasibility because you don't know where the answer is. So you're going to say add. I want to make sure that the clearance is greater than or equal to 0.25. That's what I want. I want the clearance to be always equal to 0.25. If you know that you want to increase the volume, so you can go optimize, maximize the volume calculated by the volume calculation. I want that to be max. Now, right now, what is the value? You can quickly go type in volume. You see, that's the volume that calculates. So when you go ahead and optimize, so you want to maximize the volume, that should be the clearance. So in order for me to do that, I'm going to change some variables. Notice that this is like a 3-bar linkage example. So you can quickly go ahead and pick certain dimensions. Hey, I want to pick the overall length of the rod. I want to pick that hole. You want to also go ahead and pick the overall length of this link. You might also want to pick the hole position real quick, 1 second, add a dimension. Hit the grid, it doesn't let me pick it. Come on, buddy. So let me just pick the rod assembly, rod part. I'll pick the right dimension here, guys. Just give me a second because it wouldn't highlight it for me. So I'm going to go ahead and say that's the part, but I want it for that dimension. Just give me a second real quick. Link. There you go. Looking for a distance between this hole and that little hole over there. Trying to find out that belongs to the link part. So in the protrusion, that's the link. So let's look at that. There you go. That distance. Sorry about that, guys. Just won't let me pick very easily. So there you have. So you have a dimension that's overall length. You have a dimension which is the length of this link, and you have a dimension for that whole position. So I'm going to go ahead and vary it from, say, 7 to 10. I'm going to vary it from 6 to 10. You note that I've already run some sensitivity studies, so I know what the ranges are, right? So basically you see that you want to maximize the volume, you want to maintain that clearance to be at least 0.25, and you want to vary the dimensions over this range. So now you go ahead and hit compute. What it is going to try and do is it's going to give different values to these dimensions that we picked, such that our volume is maximized to the highest value. Okay, so it's going to go through the optimization. You can also choose to show the graph. I'm not showing the graph because you know, my graphics issues that I have with my computer, and also when I run a GoToMeeting, it kind of like eats away my graph. So you know, it's going to wait for it to almost get done and then start populating it. So you could see, you know, my graphics is not as good when I'm connected to GoToMeeting. So it's running through the optimization real quick, and it's going to try and reach a value which is like, you know, constant, where, you know, my graph cannot grow or increase in volume anymore. You can see the value of volume right here. So it's going up to 34 in the second pass. It's still increasing, so it's going to try to make sure that it improves that value as it goes through the optimization. So just about 10-15 more seconds, it should be at a point where we should be good to go. Alright, sorry about the wait. I hate that silence as when we are waiting for it, but this is a little bit of, it takes a little bit of time. It's almost done. In about 5 passes to 6 passes, it should be done. So there it is. Just give me a second. The thing is, this is not like an FEA where I can run it and have the result ready and here you go, boom, show it to you. So you could see that the graph is no longer increasing or improving. You see it kind of hits a plateau right here. So it's going to stop right now and kind of show you that, hey, no, I cannot improve the design anymore. but you could see the volume that was at around 25 or 27, it kind of went up to almost like around 50-ish. So let me get rid of this. If anybody wants to look at this particular relation, I'll leave it on like that for a second. Right. So it's just volume of feature ID, volume colon feature ID, and then the name of the feature. So, all right. So here it kind of like converged to a solution. Notice that it couldn't improve it anymore. So this is what you're looking for in optimization, where the solution cannot be improved anymore. So you reach a flat value. You can see the value for volume. You can see the clearance value, that's about 0.25. You can confirm and keep it. You can go ahead and look at any of the values in terms of, say, this whole. You can do an edit. You can see it's 9.36. You can look at the length of the link. It's about 9.9. Also, the length of the handlebar, which is right here, which is what we used, and that went up to 18 from 22. So this kind of gives us like the most optimum volume in terms of this one stroke analysis. All right. That's pretty much it for me, guys. This is what I had. I wanted to show you some BMX with like I said, we went over the mass property analysis, we went over center of gravity optimization, we went over volume optimization, we went over clearance and using volume optimization, we went over using an Excel force analysis, we went over using FEA and doing structural analysis within ProE by using an existing FEA. All right, so that's pretty much it from me. Can you guys open it up for questions, please? Sir?
Yes, they can ask any questions they want. I think there might be some on there. Can you see them?
Trying to see. Not in the chat.
Okay. The only question I got was what version of Creo will be used for this webcast, and I think that's probably been answered. Creo 2.0. So.
Yeah. All right. If there are no more questions, then I gotta head out to another meeting. Oh, okay, we got one. We got one. Why did the length of the handle change? Oh, I used the length of the handle as a dimension to change. You can see, I don't know if you can see this, see the handle length. I've used that as a parameter to change. It only changed the parameters that I've chosen over here. All right. Anything else? Alright guys, so I'll go ahead and take off. I have another meeting to run to. I hope this was good, and I'm welcome to any questions, suggestions. Please feel free to email it to us and we'll make sure we get them answered. Alright, sir, over to you.
All right, if anybody has any questions regarding training, if you have any interest in training, you can always feel free to email Rosalinda, which is her email should have been available on your invite. And if you ever need to go back over this video, you can go see it on YouTube. We'll try to post it this afternoon. All right. Thank you, everyone, for attending.
All right. Thank you, guys.
The organizer has ended the session.